start by saying a bit about me. So I'm currently on my first year of my PhD. I'm doing maths and in particular algebra. So I'm going to be talking to you about something vaguely related to what I do. Okay, cool. Before we start, I've titled the talk "How Many Holes Does a Straw Have?" So I feel like I would like to gather people's opinions on that question and then see whether that changes throughout the talk. So also gives me a chance to test whether this poll function work. So hopefully you should be able to see a poll on the chat. Oh yeah, I think I'm getting some responses. Okay, well, people vote. I'll just say a few other things. So basically, feel free to ask any questions at any point. I have the chat in front of me so I can see them and hopefully answer some of them while we go. Also, before, has anyone heard of algebraic topology or topological data analysis before? Can people just put something in the chat so I know it's working? Yes. Okay. Yes and no. That's great. Well, if you have, hopefully you've learned something else. And yeah, I like the not yet. Not yet. Exactly. Exactly. Cool. Okay. So currently the poll is sort of split between 1 and 2. I don't know if people can see the results, but no, I'm just telling you. About 2/3 of the people say that straw has 1 hole, and the other 1/3 of people say it has 2. So hopefully we'll manage to resolve that question. Okay, cool. Now, let's get on with it. So basically, so some of you said you've heard what algebraic topology is before. So can anyone, put in the chat what sort of ideas you have from what you've heard before? What do you think is algebraic topology is? What have you heard? Some of you say no, but some of you said yes. Topology of a geometric shape, yeah. So I guess the first thing that I'm going to say is sort of, maybe you've heard the word topology before, maybe you haven't. Surely you probably have heard the word geometry. And so I'm just going to say a bit about what is actually the difference between topology and geometry. So both have to do with shapes, right? So in front of me, there's 7 pictures actually of some shapes. But we need to be slightly more precise. And that's what I think someone's saying there. You need sort of, is this idea that topology allows shapes to be flexible, right? Whereas geometry doesn't. So in geometry, a square and the circle are two completely different things, right? Whereas in topology, we allow a circle and a square to essentially be the same because, well, you can slowly deform a square by removing its corners and making it into a circle. So topology is the study of which properties of shapes are actually invariant under deformation, right? So hopefully we can all agree that a square and a square and a circle both have no holes, even though they're different shapes. So the study of holes is an example of something that algebraic topology studies. Yeah, so some of you might have seen the cup and donut analogy. If you haven't, I really encourage you to look at the GIF on Google. Okay, cool. So yeah, algebraic topology really, where does the algebra come on? So the topology is talking about shapes up to deformation and sort of imagining they were made of like rubber sheet or something like that. Now, the algebraic is telling us about how do we actually tell these shapes apart. So I have 7 different things here. Now, can anyone think of things of some characteristics or some features of these shapes that allows us to tell them apart? So like, how can we tell apart a line from a square, or like the circumference of a circle from a circle? Any ideas? Okay, someone said 3D or 2D? Dimension, yeah, exactly. So dimension is a great example. This is an example of an algebraic invariant. Whenever we have two shapes, we can associate to them a dimension, right? So we have, first of all, here we have a bunch of points. We say that points have dimension 0. Then we have a line, and you may have heard a line has dimension 1. Then we have a square, which is sort of a 2-dimensional shape. and then we have a cube, which is a three-dimensional shape. So dimension is an example of an algebraic invariant, is some sort of feature of these objects, which allows us to distinguish them from one another. So that's, yeah, exactly. That's an example of one thing that algebraic topology studies, dimension. Cool. Let's see. Some people are saying corners, vertices, sides. Okay, yeah. So that's exactly, that is what I was talking about before about the difference between topology and geometry, right? So telling apart a corner is actually something that's quite hard because, well, what really is a corner? And that's something that algebraic topology does not study. In fact, algebraic topology takes the point of view that actually we don't really care about corners. Let's just pretend that we can smooth all the corners and like just work with like this world where like a square and a circle we're really considering to be the same because fundamentally they are the same. They both have the same dimension. They both don't have holes. We can sort of stretch a bit the circle and pinch it some corners to turn it into a square, right? Now, someone also said number of holes, and yeah, exactly. So that is something that is much more clear in these pictures, right? So like, how can we tell apart, for example, a filled-in circle from a circle that's not filled in? Well, because one of them has a hole, but the other one doesn't have a hole. And I guess maybe I'd ask, what is a hole? It's not an easy question, but it's an important one. Don't know if anyone has any ideas. And also, how about other things? Because you can say, for example, how can we tell apart a sphere from a square? I mean, I guess the question is, well, does the sphere have a hole? I don't know. What do you guys think about these? Okay, someone's saying loop in a material. Yeah. So we'll get onto how to actually define that later. It's a hole maybe whether there is a boundary in between the material. Yeah. So these are great ideas, and this gives rise to both. There's different ways of defining holes, and both of them work, and I'll say a bit about them. Um, Someone said a square would be equivalent to a square to a circle. Yeah, exactly. In topology, that's correct. Hole defined by a boundary separated into spaces. Yeah, yeah, yeah. Okay, so these are sort of all these ideas about holes. So I think okay, we've reached the conclusion that holes are actually something quite important. Before we move on, let me just say another obvious one is number of pieces, right? So for example, how can we tell apart, say, 1 point from 3 points? Well, just by counting, right? So this is another example of a very simple algebraic invariant, right? Just so in maths we call them connected components, which is how many pieces do we have. So we can tell apart one line from two lines because, well, one of them has one connected component and the other one has two. Cool. But let's move on to something more interesting, which is, well, what is a hole? So before we do that, let me just pass it over to you. How many holes do each of these objects have? So they're meant to be, just in case the picture not very clear, a straw, again, a t-shirt, a pair of shorts, a CD, like a fish bowl, and then you can think of it as a donut, but I want you to think of it as just the surface of a donut, which is probably not a very realistic donut because, well, they have dough inside. But suppose that you could say, remove the inside and just consider the surface of a donut. So if you were to paint it or like glaze it with icing or something, that's what I mean. Okay, and I would also like to see some reasoning. So not just the numbers, but why do you think they have the number of holes that you think they do? Okay, so there still seems to be a bit of controversy of whether a straw has one or two holes. And someone's saying t-shirt one. Okay, that's interesting. So someone's saying that it's just one big cavity, but it's just in a funny shape. So I guess maybe what is the difference between a hole and a cavity? Um, a shirt has a single hole, so it could be oriented into a shirt with one hole. I'm not sure what you exactly mean by that. But yeah. Okay, so let's maybe focus on just one. Let's focus on the straw first. So the people who are arguing one, why do you think it just has one? And the people who are arguing two, why do you think it has two? So someone's saying if you squash the straw, then it would be a tube with a single hole. Okay. So I guess maybe let's start with one that is maybe less controversial. How many holes does a CD player, as a CD have? One. Okay, so everyone seems to say, yeah, cool. Why does it have one? Well, because it has a hole in the middle, right? And no one's trying to think it has two. Now, what is the difference between a straw and a CD topologically, right? So like imagine the straw is like bendy. The straw is longer, yeah. The length, yeah. Yeah, that's good. Yeah, so I like the argument, right? Suppose that you have a straw and you start making it shorter and shorter and shorter and shorter and shorter. Well, if you originally argue it has two holes, then if you make it slightly shorter, surely that shouldn't change, right? You should still have two holes. Well, then make it even slightly shorter. And then how about even slightly shorter? At what point? Now, when you've removed enough straw, you're going to end up with something that's essentially look like a CD. And so then you argue that it only has one. So at some point in the middle, you need to have switched from one hole to two holes. So how does that work? Okay, the straw is technically thicker. Uh, okay. So, well, I mean, we can assume that everything is... No, I guess a CD would be thicker than a straw, right? I'm not sure what you mean by thicker. Um, but yeah. Okay, so someone's saying something is flat or not flat. So, I mean, we're imagining that things are made of like rubber, so we can sort of move them around. So really, in this scenario, a CD wouldn't really be flat. If you pick it up from the table, it would just sort of move around, right? So you can even imagine having a straw and then sort of opening it up. If you open up a straw, right, say it was, you first make it shorter and shorter and shorter until it looks like a very sort of fat cylinder, then you can sort of open up that cylinder and lay it flat down, right? And then that would be just like a CD. So the point I'm trying to make here is that actually a straw and a CD are topologically the same, right? And so from the point of view of algebraic topology, because they are the same, they need to have the same number of holes, right? So, I mean, that's something that I didn't say, but these sort of the things algebraic topology is trying to find, they're called algebraic invariants. Invariant means that if two shapes are the same, then they take the same value, even if you compute it somehow differently, right? So yeah, exactly. A straw and a CD are the same topologically. However, it's not quite the same as a donut. Um, so why is a CD and a donut differently topologically? So how could we argue that? At least intuitively. Does anyone have any ideas? Yeah, a donut has a space inside of it. Exactly. It has a cavity, right? So we think of it as sort of a straw has a one-dimensional hole, right? That's what we call a hole. But a donut has something in the middle. So do we call that a hole? Well, for now, let's maybe call it a cavity to make it different, right? Because it doesn't quite feel the same. But yeah, I hope we can all agree that a CD or a straw don't have any cavities. They don't have any enclosed areas inside it. So topologically, they are different, right? But yeah, so a straw and a CD would have the same number of holes. Cool. Now, someone's saying other things. So, for example, things like largest surface area. So that is something that geometers would care about. So if you have a small square or a big square, they have different areas. But in topology, we only care about the actual shape and not quite the geometry of it. So we don't really care about the corners or how long the sides are. We're sort of allowing ourselves to play around with that and sort of stretch however we want. We really want the fundamental shapes that govern that. And this will actually be quite useful. So I'll talk a bit later about topological data analysis and how this becomes useful. We want to be not so rigid because that's how the real world works, right? When we have actual data, data comes with noise. And so if we are able to sort of allow small deformations without changing things, that can actually be quite useful, right? But yeah, does anyone have any questions about the difference between topology and geometry? something like that. So if you've heard of it before, then you might be comfortable with it. If not, it might be a weird thing to consider. But yeah. Okay, so maybe those are the easy ones. Let's look at the fish bowl. So how many holes does that have? So I think I saw earlier some people saying one, some people saying zero. Okay, why zero? Okay, we sort of agreed in a consensus. Because it's a flat plane curled. Yep. There is no way to travel around the actual fishbowl. It's a flat surface that has been reshaped without creating holes. Yeah, exactly. Yeah. So it's this idea that really is just flat, right? And we can all agree that if you have a filled-in circle that has no holes, well, if you start making it into a bowl, at what point does it create a hole? Well, it just doesn't, right? So it doesn't really have a hole. Cool. So everyone seems to agree on that. Yeah, exactly. So the difference between a flat circle and a bowl is its curvature, right? One is flat, the other one isn't. And that is something that geometry cares about, right? But we're not really going to be considering that much today. Okay, cool. Now, let's look at the donut. So I've heard people say, well, it has a cavity in the middle. Yeah. How many holes in the same sense as a straw does it have? Some people say no holes, some people say one. Okay, could you describe the people who say one hole, could you describe where the hole is? I realize it's a bit hard to do without a picture, but in the middle. Okay, so I can try and guess what people are thinking about. So I'm assuming you want something like that to be a hole. Okay, cool. Now, how about this one here? So if you take something that sort of goes around like that, would that be a hole? Okay, why would that not be a hole? Aha, it's in a cavity. Okay, the hole doesn't open or closed. Okay, so yeah. So I said before, sorry, I'll say it again. We're assuming that the donut is hollow, right? So that it actually has no dough in the inside, which I realize is maybe not super realistic, but I just mean sort of the surface area of it. So I want the donut to have a cavity inside to make it interesting. That's the point. Um, but yeah. So someone's saying if you cut it open, it would be like the straw and have one hole and no cavity. Okay, exactly. Yeah, so I agree, that is true. Um, but then so if I cut it open um along the yellow line, then I create a straw. And the straw has that hole. So somehow, if we don't agree that the yellow thing is a hole, then we're saying that by cutting it open, we're sort of destroying a hole. Or sorry, creating a hole, which seems a bit strange. Uh, so I mean, I guess in maths we make definitions and then things will either follow a definition or not. Sadly, mathematicians have agreed that this is a hole. So a torus has two holes. The red one and the yellow one are two genuinely distinct holes. And then it also has a cavity. And yeah, a cavity is a 3D hole, but in a way that is separate from the yellow loop, right? So we want to think of holes as loops, and then cavities are a whole other thing. That is what we consider sort of, it's a bigger dimensional hole. Um, but to start with, we're just looking at sort of loops in a way. Cool. And now the more complicated examples, how about the t-shirt and the pair of shorts? Um, so maybe let's focus on the shorts first. How many holes does that have? Okay, some people say two. Why two? Some people say one. Okay, this is harder. Okay, why 1? So answers are great, but I also want some reasoning. So like why some people say 4? Okay, if you flatten out the top to become the edge, the 2 leg holes are gaps in the surface. 1 because it's one that is then split. Okay, that's an interesting point of view on it. If you stretched it, it becomes a shape. Sorry, so are we talking? We're focusing just on the shorts for now. Maybe 2 because you can squish it into a CD with 2 holes. Exactly. Yeah, okay, so let me try and just draw a picture too. So what people are saying is that actually this thing is just the same thing as if you take this circle and sort of flatten it out, then it becomes one big circle with the 2 gaps in the middle, right? So it becomes something like that, which now looks like a CD with 2 holes. So maybe this should only have 2 holes. Okay, so that's one argument for why it should have 2 holes. Some people are saying it should only have 1 because it's really just the top hole and then it's sort of split into 2. And there's some true in that, and we'll make it precise later. So yeah, this is absolutely great intuition. Okay, so now for the final one, how about the t-shirt? Aha, now someone had said something earlier. Yeah, so if you stretched it, it becomes a shape like 4 connected discs. I'm not sure how that happens. What you mean by connected discs? Some people are saying 3. So why 3? Because if you laid it flat, then you can see 3 times the arm and neck. Okay, so we can try and do, yeah, so we can try and do something similar as to the shorts. We can sort of try and flatten it out. So if we sort of maybe open it from below, then we'll have, that's a big opening, there's the hole for the head and then the 2 holes for the arm, right? And so now somehow everyone agrees that this should have 3 holes because it's, well, just the disc with 3 holes in it. All right, cool. So basically, I mean, I guess how does mathematics settle these questions once and for all is by, well, we need to agree on a definition. So the way maths works is we make a definition of what we want a whole to be, and then we can test our objects according to that definition. So you'll have great intuition. Now I'm going to give you what mathematicians have agreed is one definition of a whole. There are many others. And then we can try and see if these examples match our definition of a whole. It might just be a rubbish definition and we should just choose another one. But it turns out it's actually is a good definition. So, okay. So here I'm defining a whole as a loop that cannot be continuously shrunk to a point. So this is sort of very similar to things that you've already said. So first of all, we're identifying holes by thinking of loops. And then you guess, well, what is a loop? Well, I want you to think of it as some sort of path along the object. So you start at some point, and then you go across the object and end up at the same point. And so I want to emphasize that it's also important to sort of keep track of the orientation in which you do this. So you sort of, for the straw here, I've given you here 2 examples. Now, are both of these examples holes? Okay, so they're both loops, right? So both of the examples, both the straw and the fishbowl, they're both examples of loops. So they're both paths along the surface where you start and end at the same point and follow some orientation. The difference here is that one of them can be shrunk to a point and the other one can't, right? So you can imagine taking the loop in the fishbowl and just sort of like taking it down, 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 down until the bottom where it just becomes a point and sort of disappears. I think that is the idea. And then someone is saying, well, is holes equal to the number of loops minus 1? Well, if that was true, then there will always be infinitely many holes, right? So there's infinitely many loops because you can sort of try and sort of, if I just do this one, for example, that's another loop, or you could do, say, that one here. That's another example of a loop. So there's infinitely many loops and for infinitely many holes, which obviously this is not really what we want. We want all of these loops to be essentially the same, right? So that's the next step in our definition is to actually declare when our 2 loops define the same hole, right? So we say that two loops define the same hole if we can sort of move one along the surface, namely continuously deform one to become a different loop. Yeah? So in the example down here, we have an example of two loops. If we look at the torus, you can imagine taking this loop and sort of continuously moving across the surface, sort of like this, right? And then eventually it becomes the second loop, right? So we can continuously deform one loop into the other. And so then we say that actually they define the same hole, right? So we have way too many loops, but now we're saying that something is going to be a hole if like two holes or two loops are going to define the same hole if we can move one to the other sort of continuously. Okay, now for the second example of the plus of tans, do these two loops represent the same hole or different holes? Okay, different holes. Why different holes? Okay, so you've given me back the definition. Yeah, so I guess you could imagine uh trying to do it like just like same thing as we did for the donut. You could just try and oops, move the hole across, but at some point you realize that I mean you can try as hard as you want. This is not really gonna work, is it? Right? Like these two, they're just genuinely different. Right? If we cover the top of the shorts, then yeah, we could transform one to the other and we would essentially be back to the straw, right? Um, but in this case, they are genuinely different. And proving this mathematically is actually really hard. Uh, and I'm not going to go into any detail on how this is done because it's actually really quite hard. But the idea is that sort of intuitively, there is no way, right? If you wanted to prove this mathematically, you need to show that actually there's absolutely like, it doesn't matter how you move it, you can do all sorts of crazy things, you're just never going to get it. And so here's an example of two loops that define the same hole, and then an example of two loops that don't define the same hole. Now someone's saying, can you just keep the hole horizontal instead of tilting it? Okay, so I'm assuming what you mean is, so let me just, is kind of just sort of move this one up, right? But then the problem is that, well, now this loop here that I've drawn up here, this loop and that loop, they're not quite the same. You cannot really deform one from the other because at some point you're sort of having to jump over the other leg, right? So, I mean, does this make sense? Like they're just sort of like you cannot really continuously deform this. Imagine genuinely having a pair of shorts and wrapping some string around it. You just couldn't really push it all the way across without putting it under your other leg, right? Does it make sense? So now someone's saying, well, is the loop across the waistband a hole? Yeah, indeed it is. So it's a loop and it cannot be continuously shrunk to a point. So it is indeed a hole. Okay. There's no way you can actually shrink into the other. Okay, so there's this idea of having to split a loop in two, and I'll come back to that later. But for now, we have this sort of three holes here, right? We have the waist, and then we have each of the two legs, and they're all different, right? It's not possible to continue to deform one into the other because you would need some sort of like break something, right? So yeah, but disproving this mathematically is very hard, and it's not the point. I think the point is just to build some sort of intuition for what actually is a whole and when do we find holes to be equal and not. Okay, are there any questions about this before we keep going? Okay, I'm gonna assume that's no. So now let me go back to what you guys were saying of, well, can we split one loop into two, or what does this really actually mean? And the idea is that yeah. So actually, when mathematicians think about loops, they care about a bit more than just the hole itself, but also the loop that it came from. So in here, in the pair of shorts, we have agreed that we have one loop under each of the legs and then one loop around the waist. And these are three genuinely different loops, that they cannot be continuously shrunk from one to another. But now we can do even something that's more cheeky, and this is only something that a mathematician would care about. But suppose that you consider the first loop that you've got here, and then also the loop around one of the legs, but that goes in the opposite orientation. So you might think that these two loops are actually defining the same hole, but they're actually really different because you cannot really move one to the other with like sort of continuously and also reverse the orientation. Yeah, so does that make sense? So like if you try them moving this one across all the way up, it just would have the completely wrong orientation. Right? So really, by a definition of hole, these two would define different holes. And obviously, I'm sure we can all agree that this is silly, that it's just one hole for the leg. Right? And so we need to sort of modify this slightly. And then the way that mathematicians have figured out how to modify this slightly is to say, okay, well, we can consider loops and try and add loops together. And so we can sort of form more loops from old loops, and then maybe that way it gives us a definition to, maybe it gives us a way to actually define a hole somewhat differently. So let's see how this works in practice. So the point is that there's two basic operations that we can do with holes. We can take the negative of a hole, which is basically reversing the orientation, as for example, the CD over here. But then we can also add two loops together, which I guess is the opposite of splitting a loop into two, which is the thing that someone was talking about. And the way that we can add two loops together is by taking two loops that go to the same point, and then we just do one and then the other. And that gives us a new loop, right? So the example that we've got here is if you go along one leg and then you go along the other with the correct orientations, well, that now gives us a loop which can be deformed into the loop around the waist. Does that make sense? Okay, people say yes. No questions. All right, cool. So this means that we have a way of adding loops together, and we have a way of reversing the orientation of loops. This is what mathematicians call a fundamental group. Group is just some sort of mathematical structure where you can add. So, for example, you know lots of examples of groups. For example, the integers, right? 0, 1, 2, minus 1, minus 2, minus 3. This is something where you can add things together, and so mathematicians call it a group. Then someone's saying, so if you take into account the reverse rule arbitrary, how do we decide which way? Either direction loops completely arbitrary. Okay, no, so the point is that they're not arbitrary. It's that we have two different loops, one for each orientation, right? And they represent different loops. By a definition of hole that we had earlier, namely this definition of hole, which is why I called it a first definition because it's not a good one, they would be different holes. Right? So according to this definition, two loops with the orientations reversed will be two genuinely different loops because you cannot continuously form one to the other. Right? So now what we want to do is to actually modify the definition of hole slightly to allow us to say that actually, even though we have two loops with different orientations, they actually represent the same hole. Right? And so to make that a lot clearer, let's actually look, go back at this draw. Okay? So here there are some examples of loops in this draw. So recall that our first definition of hole was just a loop that cannot be shrunk to a point, right? So the example here under 0, this is an example of not a hole, right? It's not even a loop. Well, it's a loop, but it just stays at the same point. So this doesn't count as a hole. But all of the others are different examples of holes. And by definition, they're all different, right? So over here, we have one loop that goes around in this direction. And then over here, we have a loop, which is essentially the same, but it goes around the opposite orientation. Now, it's not possible, as I've said, to deform one onto the other continuously, because at some point you would have to like flip the orientation, which is just not something that you can do. Right? Now, how do we create more holes? So you can imagine going around this straw twice, right? This would define a loop. And then the question is, well, is this the same or different to the previous one. So I've tried to draw it here. Basically, you go around the straw, and then you go slightly up, you go around the straw again, and then go back down so you start at the same point. So then the question is, who thinks that loop number one and loop number two are really the same hole? Namely, can loop number one and loop number two be deformed onto the same continuously? So does the question make sense? Not really. Cool. Okay, so let's go back. So we've said that we're considering loops, right? Together with some sort of orientation, and that two loops are considered to define the same whole if you can continuously deform one onto another. Okay, so let's consider the following loop, that you take the straw and then it goes around the straw twice. So this is this loop over here, right? So it's doing something that looks somewhat like that. And that's a very bad picture, but. So that is a loop around the straw. My question is it possible to continuously deform this loop to the loop drawn in number one, where it just goes around once? So someone says, yes, they can be deformed if you twisted the loop numbers 1 and 2. I'm not entirely sure what you mean by that. So the same hole, because if you untwist it, it deforms into hole 1. Now the question is, how do you actually do this? So you're not allowed to leave the surface of the straw, is the point, right? So like maybe this is easier to see in a CD player, in a CD. So suppose you have your CD and you have a loop that goes around twice. So it's something that looks like this, right? Now imagine if you made this actually out of a piece of string. Now, how would you go about deforming this so that there would only be one loop? If you move both loops towards each other, they end up in the same place to become one. Okay. So yeah, I agree you can sort of flatten them out. I'm not sure if this is what people were trying to say. So you can flatten them out, but imagine this is not like this is a piece of string, right? It has some sort of width. So you cannot actually cross over themselves. I say like you can sort of cross them over, but not put them in the same place. Are we allowed to kind of destroy the city? Well, no, right? That defeats the point. So you need to do it without sort of moving from the surface of a city. Right? So the answer is no, you can't. Right? And it's again it's something not obvious, but you should imagine like if you're just sort of wrapping it around twice, you would need to sort of break something, either the CD or the piece of string, right? As someone was saying, like if you want it to only go around once. Yeah, does that make sense? And you can keep playing this game. You can take a piece of string and wrap it around the straw a million and 23 times. Well, can you untwist it so that it only becomes one? Well, the answer is not really. The only way you would have to do that is by pulling it out from the end of the straw so that it would actually completely untwist. Right? And even, yeah, exactly. As someone's saying, even if you make the CD larger, there's just nothing you can do. What you could do is remove the hole. Right? And then if you remove the hole, then yeah, I agree. You can even shrink the whole thing to a point, and then the hole disappears. Right? But the idea is that actually they're different loops. They're different loops and they define the same holes. Right? So it's actually not possible to continuously form one into the other. Right? And we're doing the same thing with the negative ones as well. If you do twice along this different orientation, they're genuinely different. And again, proving this is actually quite hard. It's much easier to prove that two loops can be deformed to one another because you just need to show how to do it. When you are trying to prove that two loops cannot be deformed to one another, then you actually need to study all of the possibilities, and that's generally quite hard. But then the point I wanted to make is that in this case, actually, I've given you all of the loops. So all of the loops that you can have in a sphere, not in a sphere, in a straw. If you tie a piece of string around the straw in any way you like, it's gonna be you're gonna be able to deform into one of these, right? Going to infinity in either direction. Now someone's saying, is there any shape which you can map a reverse loop onto an original loop? Ha. Now the answer is yes. So the most famous example of this is something called a Klein bottle, which I'm going to attempt to draw. Something that looks like this. So this is what Klein bottle looks like. So if you want, the way you construct this is by you take the straw and then you identify, you're essentially going to force both things to be the same. So you take this circle and that circle and you glue it to each other, but instead of gluing it to each other to make a cylinder, you go to the fourth dimension, you map it inside, and you sort of try and glue this end by going inside of here and gluing it from this side. So you don't glue it like this. That would be the obvious way to do it. That's boring. You don't do that. You go to the fourth dimension, pass it through the straw, and then glue it from the other side. Then you get this thing that is called the Klein bottle. And then because of this twist that you've done by gluing it from the other side, if you have very good 4D visualization skills, you can see that actually both the loop and its reverse can be deformed to the same. So if you want, as you go around the whole straw, then the loop sort of switches orientation. Yeah. But that's obviously a very hard example. But anyways, then the question then is, well, so from this example here, should we say that a straw have infinitely many holes? So is it the equivalent of a Mobius strip in a higher dimension? Yeah, so yeah, kind of. Though I mean, so a Klein bottle is just you take two Mobius strips and you glue them together along the boundary. That's another thing you can do. So sort of, if you take a Mobius band, which is something that looks not like that, like that, right? So it's this thing where you take a piece of like a strip of paper and then you glue it by twisting the sides. If you take two of those and try gluing the edges together, then you get a Mobius band, and you have way more complicated shapes in high dimensions. If this is something you're interested in, just look up non-orientable surfaces online and you'll see loads of these. And they're actually quite fun. Doesn't this mean we can't really count the number of holes, the number of loops, because then we'd have way too many? Yeah, exactly. So that is the point, right? So the thing that we've defined here is great, but because of this silly thing that we are allowed to sort of add loops, and actually, if you do the loop twice, can you spell that, please? I think what you want me to spell is non-orientable. Hope that's what you wanted me to spell. Yeah. So as I was saying, sort of, if we use this definition, then if you do the loop once or if you do the loop twice, then we should consider these as different holes, right? So then instead, what we do is we think of these as algebraically. So for the example of the straw, we would have one loop for every positive integer, right? But then we think of holes not so much as a specific loop, but more as like fundamental, like very special loops. So what I mean by this is, well, it is true that the two loop and the one loop are different from each other, but you can get the two loop from the one loop, right? By basically adding the one loop twice. And then you can get the minus one loop by reversing the orientation. And then if you want the minus three, you can get it from the one by first reversing the orientation and then doing it 3 times. So even though there's infinitely many, really there's one important one, namely this one here, right? And everything else can be obtained from this special one by these two operations that I described before, namely reversing the orientation and adding a loop to each other. And so these loops are called generators, right? Because every other loop can be obtained from the generators by doing these operations. And then a better definition of hole then can be the number of generators for all of the loops, right? Does that make sense? So if we take the definition, are loops like lines or like vectors? They're like lines. So you should think of them as sort of like, it's just a path, right? That ends and starts at the same point. Could you explain generators again? Yes. So as I was saying, there's loads of different loops here, right? And we've argued that you cannot deform one, for example, the two loop cannot be deformed into the one loop, right? So a priori, there would be different holes. Now, the way that we solve this is by saying, okay, if we look at the one loop, this is actually enough to generate literally everything else. Because if we want, for example, the two loop, just take the one loop and do it twice. If you want the minus one loop, just take the one loop and reverse the orientation. If you want the minus 3 loop, then take the one loop, reverse the orientation, and do it 3 times. So actually, if you know the one loop, then you can create all of the other loops by these 2 operations of reversing and then adding loops together. Right? If you want the 0 loop, you take the one loop, you take the minus 1 loop by reversing the orientation, and then you add them together, that gives you the 0 loop. So actually, we say that there is one hole, namely one generator, this one here, and every other loop can be obtained from this one by just sort of adding itself many times. Yeah, does it make sense? Okay. Now, people asking, what is the relation of this with knot theory? Yeah, okay, so knot theory is another branch of maths where this is very useful. So to study knots, then essentially one thing you can do is, well, I mean, the idea is very similar, right? Because I mean, we're still talking about. So for those of you who don't know what knot theory is sort of this idea of, so you can have the unknot, which is just not really a knot if you imagine tying a loop, or you can have more complicated things, which I can try and draw. Let's see how good I can do this. So you can have things. Okay, I don't think I'm going to be able to do this. Is that a loop? Oh, there's too many. Okay, you can have things that look like this. There's an empty endpoint somewhere here. Oh. Okay, no, that's not what I want to. Anyways, I don't think I can do that out of my head. But you can sort of study in space if you sort of draw a tangle of some chord and then join the two endpoints together. Is that something that can be deformed or not? And that's generally a very hard problem, but there are still spaces that topology studies, and these techniques actually do extend and can be applied to that. Okay, cool. Any more questions about this? No. So for a shape with two holes, you have two generator loops. Yeah, exactly. Yeah. So for example, an example of a shape with two holes would be the pair of shorts, right? The two generator loops are the two over here, and then the big one, well, that's just the sum of the bottom two. So the two short ones actually generate everything else. Okay, great question. What applications does algebraic topology have? That is what I was going to come to next. So one application that I decided to talk about today is topological data analysis. So topological data analysis is something that uses very heavily this idea of holes. And the way it works is, so you have some data that might come from like many different things. So one example of is all this music recognition software. So like Shazam and things like that, where like you can play a few seconds of a song and it will immediately tell you which song it is. They work using basically these methods. So you have some sort of high-dimensional data, so just like a set of, imagine a set of points in space. So the axis can be like literally any parameters. And then usually data comes with some noise, right? So, I mean, it can be something as easy as sort of truncation errors, right? Like you just haven't recorded enough decimals, or it can be that your precision is not good enough, or it can literally be whatever. But sort of data tends to be quite noisy and not very precise. And so there's a way of analyzing this data using algebraic topology, which is sort of very stable. As in, like if we just slightly tweak the values a bit, then it will still give us the same results. And this is obviously very useful because that's how the real world sort of works. And so I'm going to briefly explain how this works. So we start, the input to this system is just a bunch of data, right? Which you can see as just a bunch of points here. And then what we do is we're going to construct shapes from this data by imagine having a ball on each point and then sort of slowly increasing it. Yeah, so this is the four stages that I've got here. So the first one, there's just no ball, and then the gray surfaces are sort of trying to increase the radii of these balls. And then what we're going to do is we're going to connect 2 points if the gray balls overlap. Right? So in the example here, these balls start overlapping, and so then we just draw lines between them. Right? And so now we have a new shape. So this shape is made of this V shape and then 6 other points. Now we can keep doing this. Now eventually the balls are going to start touching each other a lot more. And so then, for example, these 3 points, they all touch each other. So we just draw the lines and then also fill it in because they all touch each other. And then same thing here, right? So we basically connect 2 points whenever their balls intersect. And if 3 of them intersect, then we fill in the triangle. If 4 of them intersect, then we fill in the whole tetrahedron that they span, and so on and so forth. So we can sort of construct a sequence of geometric spaces if we increase the radii, right? So, I mean, does that make sense? So, for example, in these 4 points, now they become a whole tetrahedron in sort of 3D space. Other lines are connected dots loops. Well, for now, I'm not really. I mean, I'm just thinking of these as sort of geometric spaces. So from this data, this bunch of points, I'm associating it some sort of geometric shape, which is some combination of lines, triangles, tetrahedrons connected to each other. They're not particularly nice or like good looking to like spaces, but there's some sort of spaces. We have some sort of family of spaces. So eventually, when these radii become big, 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 big enough, everything will be connected to each other, and then you just get absolutely no information. But it's not so much what the end goal is, it's more you're interested in the whole sequence of things, right? So if I just give you this set of data, one thing that you might be able to recognize is, well, it looks like a circle. You've just put some points around a circle, right? Now, how can we actually identify this? Is by using loops, right? And so if we look at this family of things, then we see that eventually we're going to create a circle, namely here. And then if we keep increasing these circles, like the gray circles, then everything's going to become connected to everything. So the circle is going to disappear. Right, so we actually are interested in the whole family of things. And then what we do is for each stage, we can compute this sort of algebraic invariance that we've been talking about. So for example, what I've called here H naught, this is just the number of connected components that things have. So the first one has 1, 2, 3, 4, 5, 6, 7, 8, 9 points, if that makes sense. Now the second one has only 7 because there's 6 points, and then the other 3 are sort of one connected component, right? And then from the next one is going to have 4, and then finally the last one just has one big thing, right? So then actually, the point is that we're transforming this sort of massively highly dimensional data into just a sequence of numbers, right? Which are sort of much easier to analyze, but in a way describe the geometry that's going on. So H1 is the thing that we've been talking about, is the number of loops. So in this case, the first one is going to have 0 loops, 0 holes. The second one still has 0 holes. Now the third one, you need to be careful. It also has 0 holes because we filled in this triangle here, right? So actually, we've sort of created a hole, but then filled it in, so the hole has disappeared. But then the last one now has created a big hole, right? And this is the important bit. Now H2 is also something that people study, is now bigger dimensional holes, which are also known as cavities, which we talked about briefly. So we don't have any cavities at first, but then at the end, there's this tetrahedron here, which sort of creates a cavity. And then it will be filled in and the cavity will disappear. But yeah, so anyways, the point is that we can go from this data set to some geometric shapes, and those geometric shapes give us some numbers. Now, why is this good? Well, it's good because if I imagine taking these data points at the start and just slightly tweaking it, so say I remove this point over here and I just make it sort of slightly go over here. The point is that these numbers will not change, right? Because the study of topology is the study of shapes up to sort of slight deformations. So if you slightly deform a point, but you're not going to create any holes or any loops. This just means that this circle that we have at the end, instead of looking like that, is going to look more like this, right? But it's still a hole. So what we've achieved is to have some sort of numbers that are relevant to the data set. They tell us some information, namely how many holes there are or how many connected parts there are. And these numbers are incredibly stable. If you just tweak it slightly, then the numbers will not change. So in the case of the songs, which I see you're all asking about, these data points will represent things like the frequency, the volume, all of these things that a microphone can sort of capture from the song. But obviously, if I'm speaking at the same time as the song is playing, then there's also noise that's going to change those factors. But the point is that these numbers should be the same, even if noise is added, right? Because you just it's going to only slightly shift the points. Obviously, if you're just like yelling at the microphone, it's not going to listen to the song and these numbers are going to be completely different. But if there's all this sort of minor noise, then the data, even though you're moving the points around slightly, the number of holes and all these geometric properties of this method are going to stay very stable. And so the numbers are not going to change, or if they do, they only very slightly. And so it still makes it possible to recognize the song or whatever it is. So yeah, does that make sense? Outcome points on a 2D plane. Great. Okay, so we're not really thinking of these points in a 2D plane. That's just my screen is only 2D. You should think of these planes as sort of lying in some high dimensional space. But yeah, no, I agree. In 2D space, you cannot have a cavity. Those are the properties of the song, and then the shape is the actual song. Well, I mean, no, obviously the shape is not the song. So the song, you struck some properties, and those are the points, right? And then from those, you create some shapes, and then you create a sequence of numbers, right? Now, comparing the songs is very hard because obviously, if you play the volume different, that's already different parameters. The point is that these minor changes do not affect the numbers that we get at the end of this process. So topological data analysis is some sort of machine where you feed in some high dimensional data and it outputs just a sequence of numbers if you want. And the point is that this sequence of numbers is very stable. If you tweak the input slightly, the sequence of numbers doesn't change. And so in particular, if you have some sort of like noise in the room or anything like that, then but it's still the same song, the sequence of numbers that you get at the end should be the same. And so you should be able to trace back that it's the same song, even though the actual volume that it was played was slightly different and things like that. So various quadrants of the dots is the position of the dots in several dimensions. Yeah, exactly. Yeah. Okay, someone asks, is this something you would study if you studied maths at uni? Yes, absolutely. So there's things from like groups, very basic that you see in first year to maybe, I mean, topological data analysis might be something that you see maybe in later years because it takes quite a lot of stuff to build up. But certainly sort of algebraic notions, how to tell spaces apart and topology and geometry and all of that. Yeah, you get loads of these. I mean, I've learned all of this stuff in my when I studied maths at uni. So